My talk is called A Domain of Unital Channels. So, since this is mostly, it seems, a physics crowd, I feel I should go a little bit into what domain theory, like how it sort of came to be and why it's interesting that unital qubit channels turn out to be a domain. So, domain theory was invented by Scott in the late 1960s and through the early 70s, early mid-70s. Most of the work was done while I was here at the faculty at Oxford. And, yes, I didn't even know that you were sitting here. Wow. Well, this is even more terrifying. No, I'm saying, please correct me if I get anything wrong. But the large thrust of domain theory was to provide a formal mathematical model for understanding programming languages, so we could actually start proving theorems in a rigorous mathematical way. And domain theory provided the first formal model of the untitled random calculus. So the realm of domain theory for a very long time rested in theoretical computer science and understanding things like denotational semantics and programming languages. So it was surprising when later on Key Martin and Bob Koka, who are also here in the audience, discovered that there's an ordering on quantum states that shows that there's domain theoretic structure also in quantum mechanics. And maybe coincidentally, they did this work also while they were doing postdocs here at Oxford. So that's what my talk is going to be about today, is showing a little bit more domain theoretic structure that's popping up in quantum mechanics, because the order that Bob and Key show on quantum states extends to an order on quantum channels that also turns out to be interesting in a domain theoretic way. There we go. So the basic outline is, the first part is probably completely unnecessary. I'm sure everybody here already knows all the things there, but for the benefit of the camera, I'll briefly cover some of the basics, and just to make sure that we're all on the same page with terminology. Let's start out with quantum states and qubit channels. So omega n, when I say quantum state, I mean density operator, so Hermitian positive semi-definite linear maps on a Hilbert space with unit trace. And when I say qubit channel, I mean a CP map on omega 2. And there's a well-known isomorphism between omega 2 and the unit ball. This is called the Bloch representation. So when I say quantum states, for the purpose of this talk, we just need to think about vectors in the unit ball. And every qubit channel, as a result, induces a map from the unit ball to itself. And this is called the Bloch representation of a qubit channel. So what do these look like? They look like affine maps. He mentioned these earlier in his talk. So they're just 3x3 real matrices, M applied to a vector x, and then plus a vector that lies inside the unit ball. But not every affine map on the Bloch sphere, we call B3 the Bloch ball, not every affine map on the Bloch ball is a channel. There was a paper by Mary Beth King and Christopher Riscott that characterizes which of these actually correspond to qubit channels. It's a very hard problem. And we call a qubit channel unital if it fixes the origin. So he also mentioned this a little bit in his talk. We can think of these, if we think of this constant B as a measure of how much bias is injected into your quantum system by the channel, the unital channels are the unbiased channels. And there's a very nice decomposition of these. This was also described in that same paper by Mary Beth King and Chris Ruskai. But they just sort of describe it, but they don't really formally lay it down. So I'll formally lay down exactly what this decomposition is. It's based off the singular value decomposition. So what does that tell us? And now it's easy to see that if is a Unital channel if and only if the diagonal part of this decomposition is a Unital channel. And that's just because composition of channels is a channel. So if it is a Unital channel, we decompose it into R1 times this diagonal part times R2. Then R1 inverse and R2 inverse this diagonal part. So that's a channel. And conversely, if R1 times the diagonal, if the diagonal is a channel, then R1 times the diagonal times R2 is also a channel. So what do these look like? What do the diagonal channels look like? This is the Bloch representation of the spin channels, and if you take the convex closure, we get the set of diagonal Qubit channels, or the diagonal Unital channels. These can be pictured as a tetrahedron in R3 with those given vertices. So it's a nice geometric way of picturing them. So what can we do with this? It turns out one of the really nice things is very hard problems for general Qubit channels tend to have nice solutions in the case of Unital channels. This this is Holevo capacity. In retrospect, like looking at the list of people here, I maybe should call this the Holevo Schumacher-Westmoreland capacity. I hope you all don't mind. But it's defined like this. I shouldn't really say defined, it's quite a lot of proving, right? As members of the audience could attest to.
Sum of x is equal to 1?
Yes, the sum of the xi's is equal to 1. Or, yeah, that's right. And this is a notoriously hard problem to calculate. Well, it's a notoriously hard value to compute for general Qubit channels. But it's been proven in several cases for Unital channels, or in several different places for Unital channels. It turns out this is a solvable problem. So if F is a Unital channel, we decompose it into R1 lambda R2, then the capacity of F, it's easy to show, is equal to the capacity of that diagonal part. And the capacity of the diagonal part is just this value, 1 minus h of that, where h is Shannon entropy.
Lambda was the smallest of eigenvalues?
Lambda 1, it's not the eigen, it's the largest singular value. Yeah. So one thing that I want to point out is that this capacity is not a very constructive thing. What I mean is, even if somebody hands you an ensemble that you can use to achieve this capacity, it still doesn't tell you how to implement a protocol to communicate at that capacity. It will tell you something about how you're supposed to encode in order to communicate at capacity, but it tells you nothing about and this thing is computationally complete. By that I mean, if you have a computation on the domain that converges to an answer on the domain, or that converges to an answer, then that answer is also in your domain. It has an intrinsic notion of approximation. Approximation tells you when one piece of information is essential to knowing another piece. And any object can be recovered from the things that approximate it. So what do we do with quantum states? Well, we have to start with an ordering of classical states. So to do that, delta n is the set of probability distributions on n outcomes. And we define projection operators on delta n by basically, if I have a probability distribution and somebody tells me that it is not the ith outcome, I just delete it and then rescale the distribution. And the order on classical states is defined inductively. So on delta 2, we have 1/2 blissfully at the bottom, the state of complete ignorance. And then we have 0, 1, and 1, 0, the states of complete total knowledge that you know what the outcome is on top. And going up along either side is going up in the order. And then we inductively define it by saying, I know more than another person does if whenever we're both told that it's not the ith outcome, and we delete that from what we know, that I still know more than what the other person knows. So Key and Bob showed that this is an order on delta n, and they called it the Bayesian order. They actually showed several more interesting results, but we only need the fact that it's a partial order for here, because we use this to get an order on quantum states. Now, here's some stuff that I will insist you don't read, but here's how to think about it. We say that if I have two states that describe two systems, two states, rho and sigma, that describe two systems, then one state is more informative than the other state if there exists some experiment that I can perform on both systems where the outcome on one system is more predictable than the outcome on the other one. And more predictable means larger in the Bayesian order. Now, Key and Bob also showed that this is a partial order on omega n. And they showed that it has some interesting domain theoretic structure, and in particular, omega 2 is a domain. So the question is, what does this domain theoretic structure teach us about qubit channels? Because we have qubit channels now that are functions over a domain. So the first question was, I just ruined it. The first question was, which qubit channels are Scott continuous? So a Scott continuous channel is, or a Scott continuous function is one that's monotone and preserves correctness suprema. Think of these as functions that preserve computations. So it turns out that a qubit channel is Scott continuous if and only if it's unital or it's constant. So the Scott continuous channels are the unbiased channels or the completely biased channels. Now, since omega 2 is a domain, then a classic result in domain theory tells us that the Scott continuous maps over it in the pointwise order also forms a domain. But the problem is that the Scott continuous qubit channels aren't all of the Scott continuous maps on omega 2. We don't really know how they sit in as a substructure. So we can't really use this to tell us whether or not the unital channels form a domain. But it turns out that they do. The Scott continuous qubit channels form a domain. And in particular, just the unital channels by themselves form a domain. The way we show this is by using this decomposition. So the first thing to notice is that rotations are order isomorphisms on omega 2, meaning just if I have rho and sigma, and rho is below sigma, and I have some rotation r, then r of rho is below r of sigma. And because we're using the pointwise order on channels, this means that composition by rotations is an order isomorphism on the space of unital channels. So now if I have two channels, f and g, then f is below g if and only if this function here is below a diagonal channel, lambda. channels are Scott continuous. Which ones am I talking about? Well, here's a stupid example to start with, right? F goes to F transpose is Scott continuous. Well, that's, kind of dumb. Also, F goes to any statistical mixture of F and its transpose is Scott continuous. Conjugation by unitary is Scott continuous. And if we send a channel to the diagonal part of this decomposition, that's also Scott continuous. This one we have to be a little careful with. Lambda is not necessarily unique. The decomposition, the diagonal matrix in a decomposition is not necessarily unique. But we know it's either going to be the positive, either the singular values down the diagonal or their negatives down the diagonal. So if we just make the convention that we send a channel to the positive part, if there are two ways of doing it, then that's a Scott continuous operation. These things are just operations that, as we're trying to solve problems with Unital Qubit channels, we use these to reduce our problems to solving ones on diagonal ones. And it turns out all these things are Scott continuous. So maybe coincidentally, maybe not. Also, any measurement on U is Scott continuous by definition. So what are measurements? A measurement, the idea of a measurement is that it's a Scott continuous function that gives you a way, in domain theory we have a qualitative way of saying when X is more informative than Y. A measurement is a function that gives you a quantitative way of saying how much more information. So here is a definition which I also insist you don't read at this point, but if you're interested you can consult the literature. Examples of measurements: Holevo Schumacher-Westmoreland capacity is a measurement. Setting a channel to its norm is also a measurement. And this function is a measurement, where you probably recognize this function from a few slides back. Right? This was the function that characterizes the maximal elements. So I'd like to talk about that one a little bit more. It's called a natural measurement on Unital channels. It has several nice properties. For one, the kernel of the measurement is equal to the maximal elements. Secondly, it gives us the entire range of numbers we can multiply a Unital channel by and still have a channel. And in particular, it gives us a way of finding the unique maximal element above any channel. Also, if we extend the measurement to all 3x3 matrices, then the set of Unital channels is exactly the inverse image of 0, 1. So the Unital channels are completely captured by their natural measurement, which is, kind of an interesting thing. I'm not sure what that means just yet, but I'm sure it means something. And I kind of blew through this fast talk kind of quickly because I'm trying to get us a little back on track. But, if people want me to say a little bit more, I definitely can. Here are some things to think about for the future. It's now shown that all channels, all Qubit channels, form a Scott. When I say Scott domain, I didn't define what Scott domain is. I forgot to delete the Scott part from this slide. But I just mean a bounded complete domain. If there are other domain theorists in the crowd, please don't jump all over me for omitting the algebraic part of the definition. But all Qubit channels form a domain as well. But the order is not as nice. Things happen like Holevo capacity is no longer monotone, so it's definitely not a measurement. And it's very hard to. It's not very satisfactory the pointwise order on all Qubit channels. So one thing that I've been wondering is, we know lots of possible orders on Qubit channels. Can we find them? Do any of these give us a domain theoretic structure where potentially Holevo capacity would be a measurement on it? And in particular, it would be nice if Holevo capacity was a measurement and its kernel was equal to the maximal elements in this order. That's a very good question, and I don't know exactly, what the correct notion of computability on these are. Like I said, on the more general, if we extend the order to all Qubit channels, it doesn't seem to be a very satisfactory order. So it feels like, we haven't found